Thanks to the organization and everybody for having me here. I could have some stories to tell, but I'm not going to tell them in detail. But what I'm going to talk about comes from some of these stories. Basically, when you have to, or in the past 10, 15 years, where we have had projects with companies with about what was called data mining, and now we refer to data science, even if both things are not the same. You have to do a lot of things about data integration, data cleansing, data wrangling, and a lot of these things. Finally, they take a lot of time, but they are sorted out. Okay? So in one way or another, these things are sorted out. So the big problem for some of the experiences that we have had in the past is that a complete project, even at the end of the project, can be spoiled because you don't recognize the utility or the way the project or the models have to be deployed. So you have a very bad understanding of how your models have to be deployed, how they have to be assessed, then the whole project is jeopardized. And that happens a lot of times, and I've lived that, and it is from that experience that I have just come up with a series of pitfalls, caveats, and then I'm going to just talk about some tips that we have gathered in the past years. Of course, you can find some of these in any machine learning or data science textbook, but I think it's important to emphasize them because some people just think that you just take a model and you just do evaluate with your preferred metric, and that's the end of it. And that's a crucial point. The crucial point about a good model is how well the model is evaluated. About the stories, there was some of the stories that we had in the past. One was about a big retail company. Probably you, if you live in Spain or you all have been here several times, you know it very well. But there were about 8,000 products and about 1,000 supermarkets. So the plan was to have 8 million models. Basically, because at the time, we didn't know how to have a general model for all products and supermarkets. What we realized at that point is that there were some things that were changing between one product, one supermarket. So you knew that the evaluation changed because it wasn't the same for one product, just to overestimate that underestimate. So just using this mean squared error for every product was wrong because you needed a special utility function for each model and even for each pair of model and supermarket. Okay? And so there was one thing was about evaluation, and the other thing is how can it be that we have 8 million models? Can we do with just one model for all supermarkets and products? A similar thing happened in a hospital. We had a project a few years ago. We had to predict emergency pressure, and you could do that well globally, but when you delved into specialties or areas in the hospital, you came up with different models and different evaluation metrics. So in the end, what we realized is that whenever you are just working in a problem, you have to predict, or you have to define models for different areas of that, and whenever something changes, you have to start all over again. And it is not clear that the model that just gives you the lowest squared error or the highest accuracy is going to be the best model in all of these situations. And that just suggested that performance evaluation is a critical part, and you have to bring it up front from the very beginning. And then perhaps with this, you don't do things better than without them, but at least you can reach the end and know in advance if you're going to have a success or a failure. So I'm going to talk a little bit about machine learning evaluation basics. I don't know, because there's a kind of variety in the audience. And then I will go into this idea of context, I think the previous presentation talked a little bit about context and the importance of context when you just have one model just working for this data and the data changes and then you need to know whether this is going to work for the new data. And then I will just focus on one specific kind of context. It is that your costs change and your class distribution changes. And this is just an illustration of an area where you can do things, and these things are well known. I don't know if you are familiar with ROC analysis, but I will show that as an example of the things that can be done when you just anticipate your context. You understand your context changes in advance. Okay, so let's ignore data wrangling and data integration, data cleansing, all of that. All of this takes 50, 60, 70% of our effort in a project. And just imagine that you are in a moment where you have all your data integrated and you're about to press train. Okay, that's the easy part. Well, it's not that easy. You have to choose between several techniques and parameters and all of that. But then, basically, you get your model. But the problem is that, well, what are you optimizing for? So you can say that this model is better than another, but you need to know for what then. So the important thing is not the metric, but that you realize that this is not in the lab where you want to optimize your model. It is in the real world, in the real application. And sometimes what you have in the lab is just a part or a different view of the problem, or just a partial or idealized view of the problem you're going to face in the real world. Okay, when I say in the lab, it's in your platform where you just have your data integrated and you're just training your models and evaluating your models and all that. So we need to focus on deployment. Deployment is not the test data. We will see that in a moment. So, well, perhaps you use a different, you can use the term production if you like, just to put a model into production. So that's what I refer to with the word deployment. And you can use many different metrics depending on the problem. But the golden rule, and you probably have heard about this rule, but a general version of this rule is that never overstate the performance of your model because in the lab it works well, because it might happen that in the real world when you go to production, when you go to deployment, the model doesn't behave so well. So of course we need to know the reasons why this might happen. So in the lab, we are well used to these problems, overfitting, underfitting, and it is clear that one solution for that, especially in predictive data mining is one rule that we can call the golden rule, but just for predictive tasks. Never use the data you're using for training for evaluating your models. Okay, that's clear, there's a golden rule, and nobody breaks the rule. Because otherwise you can have a very optimistic assessment of your model, and we don't want that. This is quite easy because we typically, that depends if we have time or not, but if we don't have time in our data set, we typically just make a random partition and we work with that. Of course, there are some problems here. When we evaluate, we need to choose one performance metric, and with that performance metric, we select our best model. That's common practice. That's what we do with any machine learning, data science, data mining platform. Of course, there are some caveats about this. What if we don't have a lot of data? That was solved many years ago. Well, statisticians know this very well, so you can do something like bootstrap or cross-validation. And in cross-validation, even you have, you can just make the partitions many times, and without breaking the rule, you can have that your models are trained with the whole of the data set, and they are evaluated with the whole of the data set, which seems a little bit counterintuitive before you see that this is just doing this many times. It is also important that there's no need to do cross-validation, even if some platforms just put it as a default thing when your data set is large. Okay, so this is something that, well, so is this enough to have a good model? Or just to select a good model? So, well, these are the testing conditions, quite okay. But what about deployment conditions? What's the difference between training or testing conditions and deployment conditions? Well, the difference is context. That's the difference, okay? Because basically what they are doing is exactly the same thing. The problem is that we are assuming many times that our test set is going to be, or is going to have the same distribution, the same conditions, the same context than the deployment application, the deployment data, and everything that surrounds that deployment data. And this is not usually the case. So we can have a model, then we have a context, and we know, oh, is this model working in this new context? Then we have another context. Do I need to change the model? Do I need to retrain the model? Then I have a third context, and do I need to do this again and again and again? Okay, so the question is that the evaluation of a model, can we make a model that is more versatile and can be adapted to several situations, or at least we are able to determine what's changing between these contexts and at least try to automate the things that are happening between contexts. For those of you who are familiar with machine learning, this will probably remind you of areas such as transfer learning and all of these things. So this is a little bit about that. But from the point of view of evaluation, what can we do when we evaluate a model, even if it is a specific model, or better, a general model that can work or can be adapted or reused for several context changes? Okay, so the idea is that how can we take context change into account from the beginning? The first thing that we need to realize is that there are many kinds of contexts. So I'm talking about context, but can you be a little bit more precise about what you mean by a context? Well, one kind of context that is easy to realize is that your data, you have some data where you train and test your models, may change when you try to deploy your models. That happens all the time. You just learn your model for a data set, and when you're going to apply it, you apply that to the most difficult part, or to the easiest part, or to some other part that is new compared to the part that you have learned your model. Okay? So the time the data is changing, and occasionally you can anticipate these changes, and some other occasions it's more difficult. There might be changes in the prior distributions, and there are many kinds of data shifts. Okay, many things. It can be just the relation between the input variables, the relation to the output variables. That might be different cases. There's also changes in the utility functions that you are using, especially the cost functions. In this example about the retailing company, it is not the same to overestimate than to underestimate, because you are just predicting product sales, so the costs are not going to be symmetric. That's something that is very clear from the beginning. It's not the same just to have something in stock and you cannot sell it, and just to break and you don't reach, you cannot sell something because you don't have it. Well, this is something very, so we use a squared error for this? Well, it's not the best solution for this problem. But some other changes can change, some other things can change. For instance, you can have more noisy information, less noisy, more missing data, more uncertainty in your data, even if the data has the same distribution. You can have representation changes, new variables. Some variables change in magnitude or in labels, or even you have new constraints. Some predictions cannot be done. Or you have more information about or less information about a situation. Or even your task can change completely. there's something that, for instance, one of these examples is quantification. I don't know if you have heard about this task in machine learning or in data science. You can predict how much you're going to buy, how many products you're going to buy, or how many euros you're going to spend. But I want to know how many euros all of you are going to spend. There's one easy solution, it's just to create a regression model for each of you and just aggregate all of that. And I have a global prediction. But is the way I evaluate each of these local models the best way when I want to aggregate all of these models? Probably not. Probably we need to do some adjustments. So when you change, but you can use these models. So you can just create a model you just plan to use for something, and then you realize that you can use it for a different task. So this is a more important change, but all of these changes are context changes. So you can parameterize them, you can just analyze them, and you can anticipate that these things may alter the quality of your models in deployment. Of course, I cannot go through all of them for just 20 minutes, but I will just show a few slides about rock analysis, which is just one example. I will go very, I will skip some slides here, but basically, what we do here is that you can evaluate several models. That's quite okay. You can derive many metrics for that. And then you can say, okay, which classifier is best? So that depends on the metrics. You use error, you use macro average, or you use precision, you use recall. You can do all of these things, and that depends on your models. But on many occasions, not all your errors are equally costly, so this is cost-sensitive learning, so you can just say, okay, can I evaluate or construct my model depending on a cost matrix? And you say that not all your false positives and your false negatives, they don't have the same cost. So what you can do is just evaluate your three models, taking into account that cost matrix. And from there, you can just say that this is the best model because according to my utility function, this is the best model. So in this case, if we have a context, this context is just defined by the cost matrix and the proportion of positives and negatives, I can say that this is the best model. But what if these things change very frequently? And that is the case. You imagine you have a recommender system, or you have a spam filter. It is not the same that this matrix is the same for each customer or for each user. You have a different matrix for each of them. So you need to think, how can I just create models that work well for a variety of models? So one technique that helps you to do that in classification is rock analysis. And basically what you do is you plot your models as points. I will skip the details. And there you can just see whether it is a good model, bad model, or just a random model. That's not very interesting. The interesting thing is that you can just connect the points because basically you can toss a coin and say, okay, half of the time it's model and this model. So you can connect the points, and when you have a lot of models, you can just plot or show these points on this space and see the sum of these models will never be optimal in any possible context. So you can discard them forever. So there's no notion of the best model because some of these models are going to be best for some context. But the thing that you can say is that some of them are not going to be optimal in any context. So basically what you do is something like this. You have a context and you say, okay, you calculate the slope, which is just given from very simple information about your matrix and the proportion of positives and negatives. And you say, okay, this is the best model for this situation. Now you have another situation and you say, okay, another context, and you say, okay, so this is the best model. So depending on the context, you choose between one model or the other. But you previously have discarded a lot of models that are not optimal in any possible situation. So the rule is that you don't get the best model. but you can discard a lot of them. And basically what you get in the end is about 4 or 5 models that you keep. So, well, I'm not going to explain how to construct a curve, especially for scoring classifiers. This is a little bit more technical, and I don't have time, sorry. Basically, we do the same here. So this is basically when you have a model predicting probabilities instead of just classes. And basically, we do the same thing. There are dominance areas where we know that one model is better than the other. So we keep 2 models here because there are some areas where one is better than the other. But the thing is, what if I only want to keep one model, the best model? Well, in this case, what we can do is, okay, can we calculate how well this model behaves in a range of contexts? Depending that we have many customers, and each customer, they are going to have different cost matrices. Can I just have a metric that tells how good this model behaves in a range of situations? Well, that's basically the area under the curve. You can calculate that and say, okay, B is much better than A. There's an area where A is still better than B, but well, in this case, it is very clear that with B, you can do very well. Nevertheless, every aggregation metric just reduces information, and it is worth just using the plots and having many models and just keeping the model that you need for each particular context. Okay, so this is just one example of something that you can find in many ROC utilities to plot the curves and to do all these things. So you can find packages for this almost everywhere. But the idea is that you can generalize that for other areas in machine learning, not only for binary classification, for regression, there are similar things. For instance, you can do this for regression, for overestimations and underestimations. So it is not just the ROC analysis, just something for binary classification. But basically, the idea is that we can generalize for some other context. Well, I will show that because I'm running out of time. The idea is that we can apply the same methodology for other kinds of context changes. So it's not just binary classification. It's not just cost-sensitive learning or cost-sensitive evaluation with imbalanced data sets and all that. You can do the same philosophy or methodology when you have some other areas and some other tasks and when you have some other context that might change. For instance, if you are expecting more noisy information, you can anticipate that and keep the model that is going to behave well when the noise is there, even if your training data doesn't have noise, okay? So that's something that you can anticipate. And there are ways to do that, and things are changing in the same way that you can just keep several models, and depending on the level of noise, you can say, okay, this model is going to be the optimal when I have 10% of noise, or when I have 20% of noise, or when I have a white noise, or I have this kind of noise. You can do that for all of these kinds of contexts that I mentioned a few slides back. Even if your task change, you can just anticipate that and keep the models that are going to behave well when you integrate all of that. So going back to this slide, basically, if you generalize what we have seen very briefly with ROC analysis to other areas of machine learning, you can see, okay, try to identify the context. Is the context changing? How is it changing? Can I parameterize these changes? And if you can answer approximately well to these questions, you can anticipate that. You can just train and specially select your models according to that context, and taking into account that these contexts are going to change. Because otherwise, if you just focus on the data and the context where you took the information, then probably you're breaking the golden rule, and the golden rule is don't overstate how good your model is, because perhaps when you go to deployment, this is not going to be that good. And basically that's it. I'm a little bit out of. Okay, so thank you.